What do multimodal robustness, long context medical video understanding, and goal-driven reinforcement learning have in common? They each reveal a deeper truth about AI. Progress is often less straightforward than it looks. In this episode, we dive into a benchmark that questions whether multimodal domain generalization has really advanced, a medical video challenge where crucial evidence is buried in hours of footage, and a new theory that unifies goal-conditioned RL with skill learning. Stay with us as we unpack where AI is genuinely improving and where it still falls short. Let's explore the first paper. Are we making progress in multimodal domain generalization, a comprehensive benchmark study? This paper argues that multimodal domain generalization has not shown clear algorithmic progress once evaluation is standardized. The authors introduce MMDG Bench, a unified benchmark spanning 6 datasets across action recognition with Epic Kitchens and Hack, mechanical fault diagnosis with Hust Motor, and sentiment analysis with CMU MOSI, CMU MOSI, and CH-SIMS, covering 9 methods, including ERM, RNANet, SIM-MMDG, MUSA, CMRF, NEL, JAT, MBCD, and GMP, across 7,402 trained models and 95 cross-domain tasks. They find that recent specialized methods usually provide only marginal gains over ERM, often below 1 percentage point on sentiment analysis, where MUSA reaches 66.6% ACC2 versus ERM at 65.63%, and that no method consistently dominates across datasets or modality configurations. The benchmark also shows a large oracle gap. On Hack with video plus audio, the target trained oracle reaches 92.81% accuracy, while the best DG method, MUSA, reaches 70.95%, a 21.86 point deficit. Trimodal fusion is not reliably better than strong bimodal setups, and robustness is fragile. Under defocus blur on Hack, mean accuracy drops by 7.97 to 12.82 points, with SIM-MMDG falling 12.82 points on average. While missing audio is comparatively mild, but missing video can reduce performance by 36.5 to 43.93 points. For trustworthiness, SIM-MMDG performs best on misclassification detection and OOD detection, but CMRF and MUSA trade off these metrics, showing that calibration and OOD separation are non-redundant. The core novelty is not a new algorithm, but evidence that clean benchmark gains have overstated progress in MMDG. Let's explore the second paper, MedHorizon towards long context medical video, understanding in the wild. MedHorizon introduces a new benchmark for full procedure medical video understanding in the wild, built to test retrieval before reasoning over extremely sparse clinical evidence. The dataset preserves 340 public videos spanning 759 hours across 8 source datasets, 7 organs, and 2 clinical settings, and it pairs them with 1,253 evidence-grounded multiple-choice questions. Its key novelty is the evidence regime. Only 0.166% of frames are relevant on average, or 1.7 evidence frames per 1,000 decoded frames, making it 169 times sparser than QV highlights. The benchmark explicitly targets fine-grained localization and multi-hop clinical reasoning, including phase recognition, step discrimination, lesion binding, count proportion reasoning, and temporal ranking. A construction pipeline combines source annotation retrieval, GPT-5, 4-question rewriting, distractor strengthening, and 3 reviewer human verification to ensure every item is anchored to traceable visual evidence. Experiments on representative general, medical, and long video MLLMs show that the strongest model, Gemini 3.1 Pro Preview, reaches only 41.1% accuracy, while most open source and medical models remain in the mid-20s. Diagnostic analyses show non-monotonic frame scaling, with more frames often adding redundancy rather than signal, a large retrieval gap between uniform sampling and Oracle GT images, weak use of temporal order, and attention drift, where models spread focus across redundant anatomy instead of sparse, decisive moments. The paper concludes that longer context windows alone are insufficient, and future medical MLLMs need evidence-aware temporal selection, contextual binding, and robust multi-hop clinical reasoning. Let's explore the third paper, Unifying Goal-Conditioned RL and Unsupervised Skill Learning via Control Maximization. This paper unifies Goal-Conditioned Reinforcement Learning, GCRL, and Mutual Information Skill Learning, MISL, under a single control maximization framework and shows that the apparent link between them is formulation dependent rather than universal. The authors identify three canonical sparse reward GCRL objectives: persistent goal, pay, gamma, exact timing, ETK, and opportunity window, OWK, gamma, and prove in Proposition 4.1 that they can induce incompatible optimal policies in the same MDP, even with the same goal and state spaces. They then define goal sensitivity, a new controllability metric measuring the performance gap between pursuing the commanded goal versus a different goal, and prove in Theorem 5.1 that for pay gamma and ETK, maximizing goal sensitivity is exactly equivalent to maximizing GCRL value, while for OWK, gamma, it gives a tight lower bound and bounded regret. In Theorem 6.1, they derive information theoretic bounds, linking goal sensitivity to goal behavior mutual information. S gamma plus matches P gamma, SK matches ETK, and OWK gamma requires the discounted first visit vector FK gamma rather than the full trajectory. Proposition 6.1 then shows that the standard MISL objective differs from downstream goal behavior MI only by the mismatch between the induced skill distribution PF and uniformity, quantified by total variation distance. The practical conclusion is precise. Pre-training with C-learning, contrastive RL, or trajectory-based skill discovery should be chosen to match the downstream goal-reaching criterion, not treated as interchangeable. That's a wrap on today's AI paper highlights. Thanks for watching.